Hello, my name is Bob Rada. I'm with HEBI Robotics. We're a spin-off from Carnegie Mellon University here in Pittsburgh, and our main product is an agile development platform for robotics. We have our roots in snake robots, and today I'm going to talk about how snake-like arms and robots are helping to automate the next generation applications in the field. To begin the conversation, I want to consider how conventional robots came to be. In fact, most industrial robots throughout history were designed with manufacturing automation in mind. They were designed to do exactly the same thing many times over with very rigid precision. As such, they could afford to be of a static configuration and fixed in place. They could afford to be very heavy and cumbersome. And this type of robot can work really well in the factory, but when you try to address opportunities for what we'll call next generation automation in the field in industries like construction and security, and applications like confined space inspection in a variety of industries, and more general industrial inspections in a variety of industries. When you try to address those types of applications, your robot needs to be a bit different. In these cases, you'll need a system that can be easily deployed in different environments. So you'll need something that's lightweight, very power efficient, and often the processes that you're automating require more human-like motion as opposed to the rigid precision that's so important for manufacturing automation. And you're also likely dealing with highly variable workspaces, so you'll need a robot system that is at least reconfigurable, but preferably very customizable. So these industries and next generation applications require different breeds of robots, which is why you're starting to see things like quadrupeds and different types of crawlers out in the field. And again, my focus for today's discussion is on snakes or snake-like robots. Snake robots have a rich and storied history going all the way back to the 1970s when Professor Shigeo Hirose pioneered snake robot research in his lab at the Tokyo Institute of Technology. His lab used approaches like active cord mechanism and created snakes with wheels, rollers, and even swimming snakes. In fact, Professor Hirose's lab spun off a company by the name of HEBI that I'll bet a lot of you are familiar with today. And there are a number of other companies that use snake-inspired robots to address automation in industrial inspections and maintenance, including OC Robotics and, of course, HEBI Robotics. That's us. And by the way, HEBI is the Japanese word for snake, which is our way of paying homage to the Japanese origins of snake robots. And one of the HEBI co-founders is Professor Howie Choset of Carnegie Mellon University. He's a robotics pioneer in his own right, and it's interesting to note that in addition to founding HEBI Robotics, he's created a number of other companies, including Med Robotics, where they develop snake robots for surgical applications. Now, there's a lot more to the history and evolution of snake robots that I won't cover here, but it's really interesting, and if you are also interested, I encourage you to view a recorded webinar that one of the other HEBI co-founders recorded earlier this month on the evolution of the snake robot. You can check that out. You can check out the recording at our website at www.hebirobotics.com/webinars. So let's skip ahead to some recent snake robot history and take a look at the work at Carnegie Mellon University that led to HEBI Robotics. And I'll start with this fun video of Howie demonstrating a CMU snake robot for Jimmy Fallon on The Tonight Show. A really important contribution of Howie's lab is work focused on enhancing the ability of snake robots to sense and control torque. This enables the robot to interact with the environment in really powerful ways, which is important for a lot of the inspections and maintenance tasks that we want to automate. So here you can see the robot using its force or torque sensing capabilities to squeeze itself around Jimmy Fallon's leg with just the right amount of force so that it can rotate and crawl up. And of course, there you saw the camera at the head as well. Clearly, that'll be important for visual inspection applications. But like I said, there's the robot crawling back down the leg again. And not all fun and games at Carnegie Mellon University. Early on, we identified snakes as a really useful solution for challenging industrial inspections applications. The robots are really lightweight, highly flexible, and have a very slim form factor, so they can effectively navigate really tight spaces and maneuver around obstacles to deliver sensors for inspections to confined spaces. As you can see in this confined space mock-up in the lab at Carnegie Mellon University, the robot can do a really great job of getting in through that tight manway and navigating around corners and around obstacles to bring that camera head to different areas of that confined space that would be difficult for a human to get to. Now, this snake robot form factor can be really useful, but it does have its limitations. On the plus side, snake robots are really capable at interacting with the environment, especially given the contributions from the Carnegie Mellon Snake Lab. Snake robots can navigate tight spaces, given that they have so much flexibility. They're typically very lightweight with a small form factor, especially compared with conventional robots that grew up around manufacturing automation. So that makes them far more easily deployable than those conventional robots. On the negative side of the ledger, snake robots are really hard to control. There are a lot of joints that are interacting with one another in really complex ways, and that presents some significant control challenges. They're difficult to build. They're very complex mechanisms, and so building a snake robot can be really quite the challenge. And from a business development perspective, there's no real killer application that's obvious for snake robots. There are a number of applications that snakes are really good at, but for most of them you can find some other form factor that would be a bit more efficient. This makes it really difficult to scale snake robots. And so as a result, what we find is that a lot of next generation robots are evolved from or inspired by snakes, but aren't necessarily snake robots per se. So with that in mind, let's go back to CMU and take a look at some additional important work done at the lab. Now in the Snake Lab, Howie and his team wanted to find ways to streamline the design, production, and control of snake robots. And in the effort, they made some key technical contributions that made snake robots more practical, and in fact made a wide variety of robots more practical. For example, typically in an industrial robot, there's a controller that tells all of the joints what to do in order to coordinate the motion of the robot. Howie and his team were early to the game in terms of exploring a more modernized approach to robot control, where there's a microcontroller at the joint level. With this type of architecture, you can have a lot more flexibility in designing new robot systems. You can still control the entire robot system from a controlling computer, but now the low-level processing can take place at the joint level, and the joints can more easily be swapped in and out. The robot can be more easily reconfigured or customized. At the same time, they developed powerful control software to manage a lot of the math behind making the robot move. This made it much easier to build and control snake robots. But then what we started to see that was really interesting in the lab is that these modular robotic building blocks found their way into other types of robots as well. So this Lego-like system that was designed to make snake robots more efficient found its way into robotic arms and crawlers and all sorts of things that started to pop up in the lab. And with this system, the team was able to create a platform for robotics that retained all of the positives associated with snake robots, those same things that we talked about a few slides ago, the ability to interact with the environment, navigate tight spaces, be easily deployable by virtue of the lightweight and small form factor. But we gained new capabilities that broke down barriers that had held snakes behind. For example, now we had the ability to rapidly design and iterate on that robotic design. And that in turn lowered development cost and made it possible to tackle highly variable, lower volume applications with various robotic form factors, snakes and beyond. So Howie and the team from his lab created HEBI Robotics to commercialize the platform and use it to address some of these next generation automation challenges not well addressed by conventional robots. And this takes us to where we are today. HEBI and our customers use the platform to create a wide variety of robots with an initial industrial focus on inspections and maintenance. And so this video you see here is an arm that we created to automate the inspection of pipe elbows and other complex geometries. So it has a UT probe at the end effector, and you recall how the system is able to sense and control torque, which made it possible for that snake to climb up Jimmy Fallon's leg by squeezing it with just the right amount of pressure. In this case, it's applying just the right amount of pressure to that end effector, which is a UT probe, to collect thickness reading on this pipe elbow. And that same process can be applied to other complex geometries. With just a little bit of information about the geometry, whether it's a pipe elbow or a T or reducer, the system can take that probe and maintain contact between the surface and the probe to collect good thickness readings. And what I find to be really exciting are the possibilities for snake robots to address some really important applications in confined spaces. Confined space entry can be really dangerous, but difficult to automate. So here are a few examples of some tricky workspaces. Here's a distillation tower with a man where he's got to lay down, and the ergonomics here can be a nightmare. I would not want that job. But somebody's got to go in there and perform these inspections and maintenance. Here's a steam boiler with some mechanical separators. There's bolts and sharp edges. Creates a really dangerous workspace. This next picture looks like perhaps something, perhaps below ground. There are some pipes that may need to be inspected. There are brackets and weld attachments, lots of things to maneuver. So you can imagine how it would be difficult for a person to get in there, but certainly for a robot to get in there. This next picture, it looks like a manway with various obstacles like plates and wiring and so forth. And in the demo that I'm about to show you, we created a mock-up that emulates a workspace that is kind of like this. This is kind of like what we had in mind, what we wanted to emulate. So with that in mind, let me tell you a little bit about the demo that we put together for this presentation. For this demo, we built a mobile base kit with a snake-like arm as an appendage built out of our HEBI R-Series actuators so that we can emulate the visual inspection of this mock-up tank that you see in the background. In the demo, we'll include the approach to the tank, navigation within the tank, and maneuvering within the tank, and then extraction from the tank. Because getting the system out of the confined space is just as important as getting in. Here's a rendering of the tank that we put together. So the robot is going to enter into that hole over on the left. It's going to navigate through a couple of plates, and the target that we want to get a visual on is that nozzle in the lower right rear, lower right on the picture in the rear of the tank. So when you see this video that I'm about to show you, you're going to see the robot from the operator's perspective. So there will be the camera view that the operator sees, and you're also going to see the top-down view. So we put a camera in this hole at the top of the tank so that you could look down within the tank to see the robotic arm navigate through those plates. So in this video, you're seeing the approach. So during any inspection, you've got to go approach the asset and make sure you're inspecting the right thing. So on the lower right, you can see the operator's view, and the upper left, you see the operator's controls. That's how they're teleoping the robot. And the arm is accessing the confined space. Now, bear in mind that this is a wide open space with this mock-up demo. In a real life environment, you're probably going to have to navigate tight space to get to the asset that you want to inspect. And so that's why it's important to have that arm be really compact and tight and able to coil up and uncoil so that you can actually get it into the asset that you need to inspect. Also note that the arm and the base are tightly integrated. So this is a good example of how with the HEBI platform you can mix and match parts. So you can mix and match arms and bases or create brand new arms. And the control software makes it easy to control the entire system as a cohesive unit. So once inside the tank, the arm can unwind and then maneuver about. Notice how it's being directed by the technician to look around at all the crevices and welds and so forth. Now I should point out here that we're doing a visual inspection in this demo, but the system is designed so that it can interact with the environment. So we could put a probe at the end of the arm and do a UT inspection or some other sort of maintenance operation if we want. And also bear in mind that this is a prototype that we put together for the purpose of this exhibit. So we're aware that in a real life scenario, the cabling should be a little bit tighter so it doesn't get caught on the sharp edges and so forth. Notice how as the arm maneuvers through the tank, you can't really hear it, but it's sort of bumped against the tank there because I've got the audio turned off. But since it can interact with the environment, the operator in this case is actually using that capability to sort of feel the way around that obstacle. So remember, we're looking down into the tank, and so it's navigating around the first plate and trying to find its way through the second plate. Again, sort of feeling his way around. We're using that ability to interact with the environment, so that's handy for the operator. And now it's going to move over a little bit, and in a moment you'll see how it identifies the target nozzle that we want to inspect. And notice how the camera remains it's sort of in a fixed position, so the arm can move around and adjust the camera so that you know what your perspective is at all times. that nozzle, the top of the nozzle is pointing up at 12 o'clock. That can be a real challenge oftentimes when you need to get a camera into a tight space. Sometimes you don't know what's up and what's down. But the system here, that snake robot arm, can maintain the proper perspective of the camera so that you can more easily navigate. Now, I mentioned earlier that there is software to take care of the math behind making the robot move. And that comes in handy in a variety of ways. It's logging the position of all the different joints at all points in time and various sensors on that robot, collecting data that could be very useful. In this case, we're using that positional information of each of the joints to track the motion of the robot, and that'll be very useful in getting the robot back out. And so we're tracking the position of the robot as it enters that confined space. In order to extract the robot from the confined space, we're just going to reverse course. And so here's a little image of the system's recording of that path. So those tools that figure out the math required to make the robot move store that information. Now when it comes time to remove the robot from the confined space, it's just a matter of reversing course. And so, I mean, think about it. In this case, the operator doesn't have the luxury of seeing where he's going or she's going by virtue of that camera at the head, unless you turn the camera around. But it's not necessary because the robot can just undo what it had already done, integrate it tightly with the mobile base to extract the arm and remove itself from that space. Thank you for your time. That's the fun little demo that we put together. I hope you enjoyed that. We had fun creating it. I want to point out that we have a booth here at ASME, RFIM. We find this to be a very informative and worthwhile conference, so we appreciate the opportunity to present here today. I'll point out that HEBI creates robotic tools, and so we've got a tremendous stable of robot tools that can create tremendous things. But what's more important is that HEBI is basically composed of a team of world-class roboticists, and we really want to know what challenges you have and what you would like to address with automation, because we really love to dig in and find creative ways to solve those things. So we look forward to hearing from you. Please visit our booth. We look forward to learning more about what your challenges are, and hopefully we can help you with that. Again, my name is Bob Rada with HEBI Robotics, and I look forward to speaking with you. Thanks.